Hello, I am Zichun Zhu from the School of Information Technology and Electrical Engineering, the University of Queensland. Today, I'm going to introduce our paper, Matching on Wireless Traffic Sensor Data with a Sequence-to-Sequence Model. First of all, I'd like to give a definition of the matching task. Matching is the process of determining vehicles' location on a digital road network by observing the trajectory data of the vehicles. In the illustration, where blue dots are the reading trajectories and the red lines are the traveling route. Here, the trajectories data can be collected from various devices, which is not only limited on one type of data. Formally, the trajectory data can be called wireless traffic data. It refers to any data that reflects the state of vehicles, including speed, location, direction, time step, and so on. Usually, based on the collection devices, we can define wireless traffic data into two main categories, object-centric and sensor-centric. Object-centric is the most common type. The GPS takes the majority in this group. It can be collected by your phones or GPS devices installed in your car. Most importantly, those devices move along with the movement of vehicles. On the other hand, sensor-centric data, particularly Bluetooth data, are collected by the Bluetooth scanner stations, which are usually installed near busy intersections, and it has a wide detection range, and it has a fixed location. Because of the different characteristic of collection devices, the data collected from them are a bit different. A GPS trajectory is a sequence of points. Usually they are very dense. So you can see as in this picture, the blue dot is the GPS readings. However, Bluetooth trajectory is a sequence of circles where each circle has a radius about 200 meters. This is high uncertainty compared to GPS. Because of this high uncertainty, the algorithms designed for GPS may not be suitable for Bluetooth if we directly use it applied to Bluetooth readings. Here's some popular methods, GPS and Bluetooth. Traditional methods, including geographic, topologic, probability-based, can usually achieve good performance, but they are super time-consuming. Also, applying those onto Bluetooth trajectory per processing is needed to eliminate distortion of readings. Alternatively, neural network-based method can take the reading sequence directly. But first, the neural network output are independent, so the connectivity of rogue segment in the output sequence cannot be guaranteed. Second, the output space is large on a large road network. So those becomes our motivations. That how can we address the problem of Bluetooth matching on a large road network? As mentioned, existing solutions are not solve the problem perfectly. Probability-based methods is too slow, whereas neural network-based methods are memory-hungry. Before our proposal, this is how to use a simple sequence-to-sequence method for matching directly. The encoder learns the pattern of reading sequence, directly takes the reading sequence and transform it into a fixed size hidden vector. The decoder takes the output hidden vector from the encoder and generates row segments one by one as the resulting trajectories. So when the row network becomes large, it raises an issue. This is the visual comparison between a small row network and a large row network. In a typical sequence-to-sequence model, one row segment takes one class in the labeling. A large row network then results in a large output space. That is not only means the large memory space requirement, but it also means the low training efficiency. To address this, we transform the representation of trajectories from the row segment sequence to turn sequence. Given this example, a trajectory can be written as A, B, E, and F. Alternatively, if we write it use turn, then it comes turn right, go straight, and then turns right from the starting row segment A. This approach can reduce the output space from 7, which is the number of rows, to 4, which is the number of turns in this example. Based on this idea, we propose the turn-based matching model. I'll introduce the model component one by one. From the top left, the input of an encoder of the sequence-to-sequence model is the Bluetooth reading sequence, and the encoder learns the correlation in the readings. In order to better represent the readings, we designed the station embedding layer that abstracts the feature of readings, including collection station ID, the coordinates of the stations. In this paper, we don't use the time step yet because it has a too high uncertainty, but we are considering to use it in our subsequent work. Then the decoder takes the hidden vector produced by the encoder. In the first time step, it predicts the start row segment, and then the same unit generates the following turns one by one. In order to ensure that the produced terms can be reconstructed to a valid road, that each row segment are connected to each other, we designed the term masking and road masking. On the other hand, the term embedding provides richer semantic information about the downstream intersections. Finally, the last layer takes the predict start row segments and predict the turn sequence and reconstruct them into resulting trajectories in the form of row segment sequence. This form is easier for later evaluation. We use two-phase training schema to train the turn-based matching. Firstly, we train the model by minimizing the cross-entropy loss and using the teacher forcing to boost the training speed, but it has two potential risks. Because we use teacher forcing during training stage, the ground truth is fed to the model. However, during testing, the ground truth is no longer available. Instead, its own prediction is fed. It raises the risk of the model exposure in two different distributions. However, during training, the model is optimized by minimizing the cross-entropy loss, whereas during testing, we focus more on precision or recall on F1 score. This is called objective inconsistency. To address those potential issues of exposure bias and objective inconsistency, we introduce a reinforcement learning optimizer component to fine-tune the matching model. We utilize the reinforce algorithm to update the parameters by maximizing the total reward on sequence, where the reward function is F1 score. Because we have no labeled real Bluetooth dataset, we generate our own synthetic Bluetooth data from high-precision GPS data on Beijing Road Network. Firstly, we match high-precision GPS data using hidden mark model and regard the result road as the ground truth. And then we random pick 141 intersection as the location having Bluetooth stations. Any ground truth road past the region will be recorded as one Bluetooth reading. In the end, we generate about 5,000 trajectories that covers about 1,000 unique road segments. For the metrics, we use position, recall, and F1 score. It should be noticed that they are all in length-based rather than pairwise-based. We compare our turn-based matching with hidden mark model, HMM, which is a probability-based model, DMM, deep matching, which is a neural network-based model. The results show that our model outperforms those baseline models. Moreover, we did some ablation studies to validate the effectiveness of each component. More detailed results can be found in the paper. And thank you for your listening. If you have any questions, you are welcome to send me an email.